Hello students, in today's lecture we are going to learn about laws of motion, NCERT section 4.9.2 and 4.10. Disclaimer: the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the content immediately. Please note that parts of the content may have been generated using generative AI, which is experimental. Learning objective: by the end of this lecture you will able to understand the concepts of rolling friction, uniform and non-uniform circular motion, centripetal force and motion of a car on a level road. So these are the important topics of the today's lecture. So in today's lecture we will cover first 4.9.2 rolling friction, after that 4.10 circular motion, and in circular motion we will cover motion of a car on a level road. So our topic is rolling motion, rolling friction. Now here question arises, how we can define the rolling friction. Rolling means when we roll something round, like a round circle. So rolling friction, also known as rolling resistance or drag, is the force that opposes the motion of a rolling object on a surface. It means when any object like a wheel rolls in forward direction as shown in this figure, and the friction acts in the opposite of the motion of the wheel. So here the motion of the wheel is clockwise and the friction that is acting in opposite direction of the motion. Here friction resists rolling clockwise here, and the friction oppose the motion of the wheel. So this type of motion is rolling motion, and the friction acts here known as rolling friction. It's a type of friction that occurs when round object, we know wheel is a type of round object like a wheel or ball rolls over a surface. So here we can say rolling friction arises when a round object rolls on a, or we can say rolls over a surface. So this type of friction is a rolling friction. Clear? Rolling friction is directly proportional to the normal reaction R and inversely proportional to the radius R of the rolling cylinder or wheel. So here R is the, small r is the radius of the rolling cylinder and capital R is the normal reaction. So mathematically we can understand it. So rolling friction is equal to mu r divided by small r. This is the rolling friction. Here capital R we know normal reaction and small r is the radius of the any rolling object like a cylinder, like a wheel. So small r is the radius. And mu r, here mu r is the coefficient. Mu is called the coefficient of rolling friction. Coefficient of rolling friction. Now we will learn some ways of reducing friction, or we can say method to reduce the friction. Clear? So first is ball bearings. Now here question arises, what is ball bearings? So ball bearings is a method to reduce the friction. Ball bearings convert sliding friction into rolling friction, which is significantly less than sliding friction. Figure 4.13a. Here the important point is this, using the ball bearings we can convert sliding friction into rolling friction. Why we here convert? Because the rolling friction is less than sliding friction. So here we choose only rolling friction. They allow for smoother and more efficient movement in rotating machines like dynamos, ceiling fans and vehicles. It means when we use ball bearings, it reduces the friction. So this is the first way to reduce the friction. Clear? Next, the second way to ways of reducing friction. So a thin cushion of air maintained between solid surfaces in relative motion is another effective way of reducing friction. Figure 4.13b. Here a compressed cushion of air between surfaces in relative motion. First, plastic disc with hole, and then air, then surface. Next method is lubricants. Using the lubricants like oil, grease, graphite, fill in the small gaps and irregularities on surfaces, preventing them from directly contacting each other. So we can say here lubricants are the best method to reduce the friction between two objects. This reduces the resistance to motion and allows for easier movement. So lubricants allows, or we can say it gives the path of an object to move easily. Circular motion. Now we will learn circular motion. This is very important topic. Circular motion is described as a movement of an object while rotating along a circular path. So using the diagram we can understand the concept of circular motion. Look at here, we have a diagram. So to define the circular motion we have a two points, point A and point B. So when an object moves along a curved path, or we can say along a circular path from point A to point B. So from point A to point B, this is a curved path. So when an object moves along a curved path, that type of motion is circular motion. Circular motion can be categorized into two main types. First, uniform circular motion. Second, non-uniform circular motion. We will learn each one by one. So first is uniform circular motion. So if we talk about the uniform circular motion, the motion of a body moving with constant speed and along a circular path is called uniform circular motion. Here in this diagram, the path is a circular path. When an object moves from point A to point B, then point B to point C, and the point C to point D, then again D point to A point, the path is a circular and the speed of an object is constant. So we can say the motion is a uniform circular motion of that object. So this type of motion is a uniform circular motion. Condition is speed of the object should be constant. Only speed. We know speed is a scalar quantity. In this type of motion, the object's speed remains constant. Look at here. If we talk about at point A, the speed of an object remains constant. Similarly, at point B, the speed of an object remains constant because this is the uniform circular motion. But the velocity changes here. About the velocity, we will learn in non-uniform circular motion. So this is a uniform circular motion. The speed of the motion should be constant. And here F, that is acted towards the center of the circular path. But its velocity. Here, if we talk about the velocity of the uniform circular motion, so its velocity, which is a vector quantity which has both magnitude and direction, is constantly changing. Why? Because the direction of motion is continuously changing. Look at here. If we talk about the point A, the direction is this one. If we talk about the point B, the direction is tangent of that point. If we talk about at point C, the direction is tangent to this at point C. If we talk about the point D, the direction is tangent to point at point D. It means the direction is changes at every point on a circular path. So we can say velocity changes continuously, or we can say constantly. So here in uniform circular motion, speed is constant, magnitude speed is constant, but the velocity will changes. So this type of motion is a uniform circular motion. Uniform circular motion. If we talk about an example, so motion of artificial satellites around the earth is an example of uniform circular motion. So also when a satellite moves around the earth, their speed is constant and velocity will changes at every point on the circular path because the direction of motion continuously changing. Clear? So the second type of motion is a non-uniform circular motion. Let's see. So if we talk about the non-uniform circular motion, so we can say non-uniform circular motion occurs when a particle moves along a circular path with a changing speed. So we have a circular path. Look at here. The speed of the particle will changes at every point in non-uniform circular motion. This means the particle's angular speed and tangential acceleration are not constant because the speed of the particle changing at every point. If we talk about the point A, at point A, the speed and direction both will be different. If we talk about at point B, the speed will changing, and at point C the speed then again changed here. At point D the speed is changed here. It means at every point the speed of the particle will change and velocity will also change. It means in non-uniform circular motion, speed and velocity both are different, means changing. For example, when a car accelerates while turning a corner, it's experiencing non-uniform circular motion because at the turning point the speed of the car is changed. Due to this, we can say this type of motion is a non-uniform circular motion. Next, acceleration. So acceleration of a body moving in a circle of radius r with uniform speed v is a equal to v square by r. Here r is the radius of the circle. So this is the acceleration of a body, and the direction of the body is always directed towards the center. According to second law, which is F is equal to ma, the force Fc providing this acceleration. So the force is Fc is equal to mv square by r. Here Fc is what? Fc is the centripetal force directed towards the center of the circular path. It means suppose we have a circular path and a car moves on that circular path, and the direction of the car is always directed towards the center of the circular path, always directed towards the center of the circle. So the force mathematically we can represent like this: mv square by r, where m is the mass of the body. So here we can understand from this equation Fc is equal to m v square by r. It means the centripetal force depends on mass, yes or no? It depends on r, yes or no? It depends on v, yes or no? So this is the formula. Centripetal force in different situation. So here we have some situations, and we will talk about on each situation. So first is a stone rotated in a circle by a string. So look at figure. We have a stone that is attached with a string and rotating like this. So when we rotate a stone, so there is a tension that is acts towards the center. For a stone rotated in a circle by a string, the centripetal force is provided by the tension in the string. So we know centripetal force acts always towards the center. So here centripetal force is provided by the tension in the string. If a stone rotated in a circle by a string. Second situation, motion of a planet around the sun. So look at here, we have a sun and the planets move around the sun. So when the planets move around the sun, there is a force that is acted towards the center of the path, or here centripetal, that is centripetal force. So centripetal force for motion of a planet around the sun is the gravitational force on the planet due to the sun. Here the centripetal force is of a planet around the sun is the gravitational force. Next, third, a car is taking in a circular turn on a horizontal road. So when a car taking turn like this, so the force that is acts towards the center is centripetal force. For a car taking a circular turn on a horizontal road, the centripetal force is the force of friction. Look at here, we have a car and the weight of the car is mg, that is which is acted vertically downward, and the normal reaction, so n equal to mg, and the only force that is friction here, F. So centripetal force is here, the centripetal force is the force of friction when we talk about the car taking a circular turn on a horizontal road. So motion of a car on a level road. There is a three forces acts on the car. Figure 4.14. Circular motion of a car on a level road. So there is a three forces. Which one? First, the weight of the car, that is mg. Second, normal reaction. And third, frictional force. So the weight of the car mg, that is acted vertically downward. Second force is normal force to balance the weight of the car, that is acted vertically upward, n. So here n, weight of the car is balanced by normal reaction. Now third force is frictional force, that is F. So here F is the centripetal force that provides, or we can say that helps for circular motion. So for circular motion of a car, we can say there is a no acceleration in a vertical direction. So ay equal to 0 because no acceleration. So n minus mg equal to 0. When we balance n, so we can say n equal to mg. So n minus mg equal to 0. Yes or no? So we can say n equal to mg. Normal reaction is equal to weight of the car, that is mg. Here m is the mass of the car and g is the gravitational constant. So we can say the centripetal force required for circular motion is along the surface of the road and is provided by the component of contact force between the road and the car tires along the surface. So here the contact force is the frictional force. Small f is the frictional force that is responsible for the here circular motion of the car. Clear? So circular motion of a car on a level road. The centripetal acceleration for circular motion is provided by static friction. So we know normal reaction is equal to mg. So there is a only force, that is F, or we can say static frictional force. So here static frictional force is responsible for circular motion. or we can say a centripetal force provided by the static frictional force. This friction holds back the vehicle from moving away from the circle. And static frictional opposes the impending motion. Here impending motion means the motion of the car, and the motion that opposes the impending motion is static friction here. So we can say static motion opposes the impending motion, the motion, forward motion of the car. So static friction opposes the impending motion of the car moving away from the circle. So we have two equations. First, static friction. So for the static friction, the Fs is equal to less than equal to mu s n. Here Fs is the static friction, and this is equation 4.14. We have a second equation, and that is centripetal acceleration. So the formula is Fc is equal to mv square by r. This one, and this is equation 4.16. Using equation 4.14 and 4.16, we get the result. So we will use these two equations and solve for a new equation. So F is equal to mv square by r, which is less than equal to mu s n. This comes from the equation 4.14 and 4.16. Now using this equation, we will solve for v. So v square equal to less than equal to mu s rn divided by m. From this relation, mv square by r less than equal to mu s n. So it is equal to mu s rg. So we know n equal to mg. So when we substitute here m cancel out. The remaining term is mu s rg. Maximum speed of the circular motion of the car, Vmax is equal to under root mu s rg. This is the maximum speed of the car, and this comes from this relation v square equal to mu s rg. So v will be what? Vmax is equal to under root mu s rg. R we know normal. R is what? Radius of circular path. Clear? Now summary. Rolling friction. It's the resistive force that occurs when an object rolls on a surface. Formula of rolling friction, Fr equal to mu r n. Here mu r is the coefficient of rolling friction and n is the normal force. Rolling friction is much smaller than sliding friction. Rolling friction is much smaller than sliding friction. Mu r, coefficient of rolling friction, depends on material, and second depends on surface properties. If the material and surface property is changed, the mu r, coefficient of rolling friction, will also change. It depends on material and surface properties. Second, uniform circular motion. So uniform circular motion means speed should be constant but velocity changing. There is no change in velocity changing due to direction changes. Centripetal force, F equal to mv square by r. So it equal to mr omega square. Centripetal acceleration, A equal to v square by r. Third, non-uniform circular motion. So speed and angular velocity both changes in non-uniform circular motion. radial acceleration, AR equal to V square by R. This is the formula of the radius acceleration. Tangential acceleration, AT equal to dV upon dt, rate of change of velocity. Circular motion on leveled road. Required friction, F is equal to mv square by R. Safe velocity, that is under root mu r g. Now we have some questions for you. Please note down. The first question, what causes rolling friction when a wheel moves on a surface and why is it generally less than sliding friction? Second, in uniform circular motion, if the speed of an object doubles while maintaining the same radius, how does this affect the centripetal acceleration? Third question, when a car takes a turn on a level road, which provides the necessary centripetal force? Fourth, in a non-uniform circular motion, if an object is speeding up while moving in a circle, what happens to its total acceleration compared to uniform circular motion? And last, which factor does not affect the maximum speed at which vehicle can safely negotiate a flat circular turn? So this is homework for you. Thank you for your attention. So circular motion DPP questions. DPP, please open with me. The first question, a car is moving on a level circular track of radius 50 meter. If the coefficient of static friction between the tires and the road is 0.4, so here coefficient of static friction is given, that is 0.4. What is the maximum speed in meter per second the car can take without slipping? And g equal to 10 meter per second square. So in this question you have to find out the maximum speed. So we know the formula of the maximum speed. Maximum speed, that is v equal to v max is equal to, v max means maximum speed, is equal to under root mu s into r into g. So using this formula we can calculate the maximum speed. Please solve. You have some time and tell me which one is correct. Just substitute the values. Mu s, that is under root, the value of mu s is 0.4 into R, that is 50 meter here, into G, that is 10. So it will be what? It is 500 into 0.4. So 5 into 4 and 20 as it is, and this one. Please wait. 200. So which one is correct? Under root 200. $14.14. Next question. A bank road is designed for an optimum speed V0 if the banking angle is increased while keeping the radius the same. How does V0 change? So here you have to find out about the V0. So we know for the banking road the formula is V equal to under root RG tan theta. So from this relation, if the theta is increased, tan theta increases. Yes or no? So leading to higher V0. It means increases. Third, a cyclist takes a sharp turn on a level road with a radius 5 meter. The coefficient of static friction is 0.2. What is the maximum speed the cyclist can maintain without slipping? So in this question you have to find out the maximum speed again. Please solve. So we know that for the maximum speed the formula is under root mu s rg. So just substitute the value. Mu s is 0.2 into value of r 5 and g is 10. So it will be what? Under root 10 meter per second. Yes or no? 2 into 10, 0.2 into 10, 2 and 5 as it is. So 5 into 2, 10 meter per second. For a car moving on a banked road with friction, the maximum permissible speed Vmax depends on what? So here you have to find out the maximum permissible speed Vmax. So if we talk about bank road, so in that case the maximum speed is Vmax is equal to Rg. About this we will learn in the next lecture. Mu s plus tan theta divided by 1 minus mu s tan theta. So here mu s, theta and r is the three terms. Mu s, theta and r. It depends on all three factors. So which one is correct? Last question. A car is parked on a banked road with angle theta now. For the car not to slip, which condition must hold? So here you have to find out the correct condition. Please solve. Condition for no sleeping. Which one is correct? Yes. Please give answer. Now submit. Now let's see the solutions. A car is moving on a level circular track of radius 50 meter, and the coefficient of static friction between the tires of the road is 0.4. What is the maximum speed in meter per second? So in this question you have to find out the maximum speed. For the maximum speed, the formula is this one. Just substitute the all given terms like static friction, R and G, and substitute the value in the formula. You will be get the value of Vmax, that is 14.14. Clear? Second question. A banked road is designed for an optimum speed V0. If the banking angle is increased while keeping the radius the same, how does V0 change? Increase, decrease, remains the same, independent of the friction. Optimum speed on a banked road without friction is this one, Rg tan theta. If theta increases, tan theta increases, and leading to higher value of V0. A cyclist takes a sharp turn on a level road with radius 5 meter. The coefficient of static friction is 0.2. What is the maximum speed in meter per second the cyclist can maintain without sleeping? G equal to 10 meter per second square. So just substitute the value in the formula, and that is, you already know, mu s rg, and this is very important. I told you this is very important, so remember this. So just substitute the value of mu s, r and g. You will be getting under root 10 meter per second square. Third question, fourth one. For a car moving on a banked road with friction, the maximum permissible speed V max depends on what? So here, just we know the formula is this one. So from this formula, this is clear that mu s, theta, and r, there are the three terms. So it depends on all three factors. So about the bank road we will learn in next lecture, don't worry. A car is parked on a bank road with theta. For a car not to slip, the maximum condition to hold is what? So that is this one, tan theta less than equal to mu s. When the car parked, weight component down and slope must be balanced by the static friction. So condition is this one. Clear? Thank you for your attention.